Can you hear me well? Also on Zoom? I hope so. Okay. Okay, shall we get started? How is the programming assignment coming along? Not great. Why is that? Say again, I didn't hear. Heuristics are bad. Anyone else? Sorry? Close to finishing. Nice. Very good. Very good. Sorry? You don't want to settle? Oh, well, do come to the office hours when we can explain that. Come to my office hours and to my TA's office hours. Yeah. But if you have any questions in particular on the assignment, so come to the office hours and post on Piazza, so we can help you with that. But to start with a few announcements and reminders, the program assignment is due this Sunday, so on 5th of February, the first assignment, and we will also have a quiz. So covering the first two modules. So so I updated the date on that on Canvas. So we'll have it next week during class. So this will be on Wednesday next week. So I chose it on Wednesday because it will be right after, soon after the program assignment is due. So you won't be stressed with P1 anymore, and you can actually have a few days to revise for it. But this will be in class. It will be a super short quiz. Like I think. We're deciding on a format, but something like 30, 40 minutes. Let's say 40 minutes. Half of the class basically will be the quiz. I think will be on paper. So actually, I probably kind of print out the sheet, and you'll basically fill it out. It'll be super easy. So this might change, but I'll let you know if that changes. Yeah, question. If we have digital notes, should you bring them printed? Yeah, you can bring them printed. It will be open book, so we can bring any kind of notes you want, printed or up to you. Okay. Up to you. You can bring an iPad with some slides if you want that. Yeah, it'll be open book. You can use a computer. Yeah. You can. Yeah. But don't count too much on it. Like it will be kind of quick. So like it'll be like half an hour, 40 minutes. Like some multiple choice, some going through like exercise and solving like problems. So like you might not have too much time to check. Yeah, but you're welcome to. Yeah. Okay. They will be quite similar to the quizzes and worksheets. you've been doing so far. So that kind of problems. So do go through them if you haven't. And yeah, and there's another one due, I think. There's another worksheet due next week, right? If I'm not mistaken. So yeah, I can go through that as well. Do they have a question there? Yeah, this one, yes, worksheet 3. Yeah. Great. So before we go into this week's topics, I just wanted so last week I hoped so Professor Gilpin went through constraint satisfaction problems with you, and sort of like by now I'm assuming you're familiar with those concepts, with like how you define a constraint problem, and if you remember the arc consistency sort of like format and those kinds of things. So now today we will start into this topic called adversarial search. So basically now we're going to assume that when we play these games, we have an adversary that we play against. And this will make it more fun and interesting and the problem becomes a bit more complex as a result of that. So we'll go through game trees, and we go through the Minimax algorithm. We'll show how Minimax basically alternates between a minimization and a maximization step depending on each opponent. We'll go into this called alpha beta pruning, which is basically a technique in which we can speed up the Minimax algorithm by choosing not to evaluate certain nodes in the tree, which we can cut off. And we'll see some more. We go through some more evaluation functions and expect max in the next lecture. So not today, but on Wednesday. So today we're roughly going to cover Minimax and maybe the alpha beta pruning. How many of you have seen Minimax before? One person. Perfect. So this is great. This is really great, because this will be new material. So do ask me any questions. It won't be too difficult, but do ask me any questions you have along the way, and we can clarify everything. So let's delve into it. So why do we care about Minimax and all these games? Like kind of like so in general, games are a form of multi-competitive environment. Is basically we have an environment, we have an agent, we have our opponents that we play against. The games can be cooperative or competitive, so we can compete with one another. They can be like what we call zero-sum games, we'll see shortly, or it can be like cooperative. We can cooperate. All kinds of games. So you've seen how you can cooperate in games in teams, for example, when you play certain teams, certain games, computer games, where you work in teams, where you compete against other teams and so on. But there's all kinds of games, and they, of course, they're very fun. They're historically interesting. Also, they're interesting, especially because they have been used in the AI field as a test bed for certain algorithms. So take chess, for example. It was basically one of the problems that we were benchmarking AI algorithms against. And it was only in '97, I think, when we made a computer that actually beat a world champion in chess, Garry Kasparov. And people were working on chess from the '60s, but it took only like around 30 years for computers to be able to beat a world champion. In the case of Go, for example, it was, we managed to do that much more recently in 2016 with AlphaGo and so on. So they are used as a test bed for assessing these AI algorithms. So you have and the idea is you have an agent, which is your agent that you're controlling. If it's a computer game, it could be like the play, you're moving around and so on. You have an environment in which this agent takes actions. We've seen this before, right? We've seen this before, and this kind of picture. And the idea is that, so what's the relationship between games and search? What are the kind of search methods we've been studying so far? So early on in the class, we went through search methods. So we went through breadth first search, depth first search, and so on. And the main idea was that here these techniques use heuristics, and they were trying to find a goal. Sometimes some of them had a goal state, some of such methods did not have a goal state. But the main difference is that with games, we have an adversary now. We have somebody we play against. Previously, when in the examples of the cities in Romania, we did not have an adversary. We just had to reach a goal state, a goal city. Now here we have an adversary. So we have to instead of finding a path and a plan, now we have to find a strategy, which is how do we play against our opponent. How do we design the moves so that we win? We have time limits sometimes to that enforces us an approximate solution. Sometimes we cannot explore infinitely the depth of the tree, so we have to stop at some point and use heuristics. We can evaluate the goodness of a game position, and that would be sort of like our heuristic evaluation from before. And there's all kinds of games. So chess is one game, checkers, Othello, backgammon, and many others. I said Go. I said this can be computer games, even like StarCraft. There can be so many kinds of games and so on. So So let's do a short nomenclature of games. So what are the here are 4 different types of games that we can have. So one coordinate is what we call deterministic versus non-deterministic or chance game. So basically, a deterministic game means that if you take an action, the result of it will always be certain. There will be no uncertainty in the state that we end up in. So for example, with chess, this is like a deterministic sort of game, because when if I move a pawn one square further ahead, it will end up there. It won't sort of whereas for example, a game which involves dice would be based on chance. So let's see some examples. So deterministic. So that's actually, before we go to that, so let's see what does this mean? What does perfect information and imperfect information means? So perfect information means that we have perfect information about the state of the game. So we know all our pieces, where they are, all our pieces. Maybe we know the opponent's pieces as well, and so on. Whereas imperfect information means we don't have full information about the state of the game, the current state where we're at. So let's see. So what kind of games are deterministic and have perfect information? So chess. So in chess, we there's no probabilities involved. There's no uncertainty in the moves, and we also can see everything. We can see our pieces. We can see our So we can see also our opponent's pieces. Same for Go. Same for checkers. So for chance, here we have, for example, backgammon and Monopoly. So you're familiar with many of these, right? So you played Monopoly before, I'm assuming. So in Monopoly, you were rolling the dice, if I'm not mistaken, and then you were So it's been many years since I played this. So that's where the chance is involved. You roll a dice and you end up with your pawn further down. You don't know how much you're gonna roll. So that involves a chance. We have games that have imperfect information, such as bridge, poker, and Scrabble. So here, that's because we don't know the cards of the opponent, of the player we play against. And also, there's some games that are deterministic, but we have imperfect information, like Battleship, Stratego, and Kriegspiel. So in particular, for example, Kriegspiel is a type of chess where you don't know the pieces of the opponent. You don't see where the opponent has its pieces on the board. So it's like they're completely invisible. So then you kind of playing. You can see your pieces, but you cannot see the opponent's pieces, and otherwise you're just following the rules of chess. So it's so that's why it's imperfect information, because you don't see the opponent's pieces. So in general, what we have in a game, we have let's say a typical 2-person game. Players alternate moves. They're often zero sum, which means that if we win a certain number of points, it means the other player loses the same number of points. If I win 3 points, the other person loses 3 points. That's zero sum. perfect information. We'll generally be working with perfect information games here in the class. So we'll have access to all the complete information about the state. And generally, no chance involved right now. If you take another class in machine learning, well, actually, maybe even here later on, we might have time actually to cover Markov decision processes, and over there we'll have basically chance involved. We can end up, if we make a move to go straight ahead, we might end up in a different state instead. So those will have more chance involved. Yeah, so these are the kinds of so tic-tac-toe, checkers, chess, and so on. These are all examples of such games. Yeah, so let's start with one game. Like, let's start with this game called NIM. How many of you have heard of this game? Okay, one person, two people, a few. So the idea is super simple. You start with a bunch of piles of tokens, and at each turn, a player chooses one of the piles. So you have two piles. You choose either one pile or the other pile, and you may pick up to one or two tokens from the pile. And the player who picks up the last token loses. Okay. So let's see in this case. So these are the two piles, pile 1 and pile 2. And you have to take, so you first choose a pile, like I choose pile 2, and then you choose how much you take from it. Do you take one piece or two pieces and so on? So that's the game. So let's define our variables that we've been talking about before as well. So our key variables that we need to define to operate in this game. So we have two players. One of them, we'll call them max and min, that will take turns. So one of them, we'll see later why we call them like that, because one of them is maximizing a score, the other one is minimizing a score. We have a state space that will define, so the state space is the set of all possible states in which the game can be in. We have an initial state, which is this, with the piles like this. We have a successor function, and we have a terminal test. So and a terminal test is when there's no more items to grab. We have a utility function that tells whether the terminal state is a win, for max, a loss, or draw. And then the max player uses the search tree to determine the next move. So say we are the max player right now, and we're gonna build a search tree. So I skip that slide. I'll come back to it. So this is how it looks. So for NIM, 2 versus 2, so you start from the max state, and you. So here this is the initial state. This is the root of the tree, and here you look at all possibilities, all possible moves you can make. So for example, so there's 4 moves here. So this is basically if I pick the first pile and take both of them out. This is this move is if I pick the first pile but take only one of them. This is if I pick the second pile, if I take one of them, and this is if I pick the second pile and take both of them, right? So these are the 4 possible moves you can make. So that's a state space. And we'll see, so this is basically what you as a player max can do, and then at this point there's next player's move, so min. So then from this point, like the min player can make another move from one of these states, and they can grow the tree further. Does it make sense? So that's another example. For example, for tic-tac-toe, so you start from the root here, which is an empty board, and then you generate what's the first possible move you can make, where you can put the X in either of these cases, and then you take one and then look at all the moves the opponent can make from here. So this is basically in the min state, where your opponent now makes a move, and so on, and you keep expanding up until you reach a terminal state, and then you define the utility of that terminal state. So it could be -1, 0, or +1, and that that tells us if you won the game, or if you lost the game, or if it's a draw. And yeah, just making sure that people can hear me on Zoom. Yeah. Okay, so so in general, adversarial games, right? So these are, as we've seen, like deterministic zero-sum games, the one that we're looking at, and we have one player that so in general in these games, so one player that we call the max is trying to maximize the result or score, and the other player, the min player, will try to minimize that same score, right? So so this is basically the intuition of Minimax search, of the Minimax algorithm. So you have the tree of the game. There's two players, a max and a min. The max player will try to maximize the score, the min player will try to minimize it. And at the end of so here at the end we will have the final scores of the game. And then, for example, like, the min will try to take what's the minimum between 5 and 6 and put it here, which is 5. This one will be 2, minimum of 2, and then max will take the max between 2 and 6 here, which will be 6. So that's basically the utility of the variable at a particular state. So so we keep and often we keep going down in depth this way, but we'll see very shortly. So let me stop here. Does anyone have any questions so far? Does it all make sense? Question there? No. Okay. All good? Okay. So we'll see that we compute these values recursively. We'll see very shortly, and here these are the terminal values. So they're part of the game, and the terminal states, which we'll use to calculate the values of these states further up. Okay. Oh, so here we go. So that was from 2 and 8 we get a 2 here. From 5 and 6 we get a 5, what I was saying earlier, and then we get a 5 up here. So the idea is that when we have this game, finding the best strategy. So when we're in a max player, we assume that our opponent is perfectly rational. So that means so the big assumption of Minimax is that our opponent will take the best decision for them. So basically, they will also go through all those states further down and basically try to compute what is the optimum move for them. So then we're going to make the optimum move given that we have a perfect adversary. This is an assumption of the Minimax strategy. So and this can be violated, of course. So sometimes if you apply this against an adversary which is non-rational, then this might not be optimal actually. So we can compute this given a game tree quite easily. So if we have the Minimax value at a particular node n here, it's either of 3 cases. So if the node n is a terminal node, we simply return the utility at that node. If n is a max node, so if it's the max player's turn to move, then we go to the successors of the node n, and we take the maximum over all the values at a particular state. And similarly, if n is a min node, we take the min over the successors. Yeah. So whatever this type of node, whether n is a max or a min node, depends on which player's turn it is to move. Is it the max player's turn to make a move, or is it the min player's turn to make a move? Let's see how it works. So we have this tree. It's a simple tree. So so we have 2 players that made 4 moves. I should say, so the notation here it will always be that we'll use this notation that will always show a triangle pointing upwards for the max player and a triangle pointing down for the min player. We'll always use this notation in the slides, so, and in our course. So in this case, so if you see the tree here starts with the max player and then it's the min player's turn. So So we have these terminal states 2, 7, 1, and 8. So first we compute the value of at this state, which is a minimum between 2 and 7, which is 2. Then we compute the value at this state, which is a minimum between 1 and 8, which is 1. And then we compute the value at this state, which is a max between 2 and 1, which is 2. Okay. And after we evaluate the states at all the nodes in the tree, we can find the optimal path that the game will take, which is this. So this is actually an important concept. So after we find these states and these values for these states, we know that the best move for the max player to make is to take this move and go in this state. And then the best move for the min player would be to also take this move and basically end up in this state. So that's why this should have also been red, but it's circled like that. So you see, so that is basically showing the optimal path that will be taken by the game. Because again, we're assuming both you are perfectly rational and the opponent is perfectly rational. And remember the definition of rationality? The search path. No, you start searching at the top. No, not at the bottom. So this is the initial state is always at the root node here. You compute the values from the bottom, yes. No. So yeah, so here you build the tree, so up until a certain depth. So this is a depth of 2. So you can build it up to a depth that is even bigger. Then you get a terminal state. You get at the depth of 2, however much you cover, you get a terminal state, which are these, and then you start going up the tree to build these values for all the nodes higher up. And yes, so that's why you start from bottom up all the way to the root. But then the actual path will be this. So you start from here, then this, and then that. And that will give you the optimal path. That makes sense. There's a question there also, yeah. Yeah. The path that it returns is different from the top. That's from the top, yes. Yeah. Exactly. Yeah. Any other questions? Yes.
It's going to search down like a certain for depth, and then it's going to see like what each state is evaluated to, like which in each like move depth, and then it's going to look at the current move, and then it's going to say which is the best move to play according to what happened.
Yeah. Okay. Yes. Exactly. So these are all possible states we can end up in, and some of them are better. Like for us, like a 7, a state of 7 is better because we are the max player. We're trying to maximize our score. Yeah, and then it's trying to find, but we also have an opponent that is minimizing our score, right? So we're trying to find what is the optimal path, what is the optimal set of actions to take to reach a good state. So it seems like the optimal path is to take this action and we reach this state of 2. Yeah. Any other questions? So one thing, for example, in chess, how can we compute these terminal states? Can somebody give me an idea? How do we compute those numbers in chess? Yeah.
Like heuristics, like what is the pieces, how many squares control, like
yes.
What is their like structure?
Exactly. A heuristic. We use a heuristic to assess the state of the board in chess. So, for example, in chess, these nodes could not be terminal nodes. It might not be a state where there's a mate, for example, in chess. you use the heuristic and you evaluate, like, for example, you can count how many pieces you have. You know, you can count the points for each piece. A pawn is worth a point, a horse is worth 3 points, and so on. So you can count up the number of points, maybe how they place on the board, and you can come up with the value of the state, and you can assess how suitable that state is for your game, and if you like it or not. Exactly. So this is the optimal play. So this is another example for another tree. Again, we have a depth of 2. We start with a max node. This is the min. This is a min node. These are max nodes again. So you see these are pointing up. These are pointing down. These are all like terminal states with all different values, and then we go higher up again. We compute all these states. Sorry for the resolution. But yeah, this is another example, but it's the same idea. So now, how do we actually do it in practice? How do we build this up in pseudo? Because it's actually not complicated at all. So it really, the only thing we need is to build up 2 recursive functions. One that's called max value, that takes the maximum value of successors. The other one is a min value that takes a minimum value of successors. And basically we define, so we do as follows. So if we define the value of the state, if the state is a terminal state, we return the utility. Otherwise, if the next agent is a max, then we return the max values over the state. If the agent is a min, we return the min values. And the max values are simply doing the following thing. So they're basically doing recursive calls. So we initialize the maximum value to minus infinity initially, and then for each successor of our state, we compute the value and then update the max accordingly. So if this value is higher than the max, then we update the max, and vice versa, and same for min. Yeah, it's I'll let you maybe spend more time at home, like, I guess, to think about it. And you your senior assignment, you might have to implement this as well in the future assignment. So yeah, so let's see another example. So we have another tree here. So all these are values for our states, for our terminal states. So this is how. So again, this is our first update. So we find the min values for each of these states. So this is a 3, this is a 2, and this is a 2. We take the minimum of all these groups, and this is a 3 again. So because at this level we take a maximum again. Okay, so is it all clear so far? Any other questions? It is a question there, yeah. You can never have too many. No, it's always because these are alternating moves. So this is based on the idea that the game assumes you alternate the moves. If you have a game in which you can make 3 moves at a time, then yes, then you can do that. Yeah. Any other questions? Are we all clear? Okay, so in that case, let's do a class exercise. So take this example, and on paper try to compute the values of min max for this tree. At every node. Yeah, let's take 6 minutes. Maybe you can make it simpler by starting with like a subtree like this, for example. You can just do this one first, and you can do some more. Is there a question there? Sorry, at the bottom. Yeah, question. What the square? What? The square is a min. Yes. So sorry. Yes. This is a min. These are all mins. Yes. Sorry. The triangle is max. Triangle pointing upwards is max. Question, yeah. So you have to run Minimax. This is actually running Minimax by hand. So I think it's quite important to do this exercise on a concept. The idea is, it's actually quite not hard. I'll explain it really quickly. So whenever you have a max player, you take the maximum of these nodes, and whenever you have a min player here, you take the minimum of the node. So here, for example, for this node, you'll take the minimum between this value and this value, which are -3 and 3. So basically, the minimum there is -3. So you put -3 here, and then at the next step here, you take the maximum between all the children. So that's fine. The maximum of a set of 1 is the same. Yeah, that's just 1. Yeah. Sorry. Maybe try going over there. Try going. It's gonna be much easier if you move in the center here. Let's see from the. Yeah. If you find it hard to see, you can come in the front here. There's many. Yeah. If you have an iPad, you can open the slides from the online. Yeah, because I have the slides online.
Professor, there's a question on chat.
Oh yeah. So there's a question on chat. I'll take it when the exercise is done.
Okay.
Yeah. How's it going? Is it almost done? Are you done? Oh. Who has finished already? Okay, almost like 50%, 60%. Okay, we'll take 1 or 2 more minutes. 1 more minute, actually. You guys done? Yeah, nice. Okay, let's see the answers. What are the answers you got? Some of you got on the top note. 1. Okay. Did somebody get a different answer? Okay, we have a few. Yeah. You got 0. Yeah, maybe double check it. That's okay. But I think you kind of you got the idea, right? How you compute them. You have to alternate between a max and a min, and keep doing that. We had so there was a question on the chat on Zoom here, which was, what is a state utility? And what is that? What is a state utility? The current state of the game. It's a bit about like the value of the current state, more precisely, not just a state. The state is the board with all the pieces, for example, but in chess. But the utility is how good is that particular state. Sorry? The goodness of it, exactly. Like how the goodness, exactly. So how good it is for us, at least, for utility for us us as a player. So can we always compute it again? If you have complete information, yes, you can. Yeah, but how? What do we do if we don't have that information? If we don't know, if we're gonna win the game or lose the game in chess? Yeah, and what do we call that? What do we call like this kind of thing of how good the pieces are? Approximation, a heuristic. So we have to use a heuristic as we were discussing in the previous lectures. So we approximate that goodness with a heuristic, because it is an approximate measure. We don't know the true measure of that state, how good, the true utility of that state. Any other questions? Okay. So let's think about the properties of min-max. So the properties we've been talking so far. So is it complete? Do we always find a solution if there is one? Yes. Is it optimal? Do we find the best solution, the best path to the tree? Yeah, we do. What about time and space complexity? So time complexity is in particular is a very bad one here in particular. So I'm highlighting the sad face. So it is exponential in the number of moves and the branching factor. So here the time complexity is b to the power of m, where b is the branching factor of the tree. So that is like how many actions we can take at each step. So in chess, it's around like 35 actions. I think I have it in the slide here. Yeah. So for example, for chess, we have around 35 moves we can make at each step. And m is the number of moves we go, and is the depth of the tree. So how many moves ahead we compute. So if you do 100 moves ahead, then we have 35 to the power of 100, which is a lot. It's completely unfeasible to be done with current computers. So we cannot do more than 100 moves ahead, and even less. So that's why we have to rely on heuristics. We'll never end terminal states in our tree, for example, for chess. Space is not too bad. It's just b times m. So so this is a min-max. I've gone through this quicker than I thought initially. So any questions, any clarifications? Okay. So let's start the next lecture, and we can continue next time, which is on alpha beta pruning. Sorry. Yeah, that's not adversarial search part 2. Okay, so part two. So we've seen this. Yeah, seen this. Okay, so alpha beta pruning. So what is this about? So the one big problem we have with Minimax is that it's it takes a very long time to compute, and it's very expensive in the number of steps ahead it needs to take. So it's simply, as you've seen before with time complexity, it simply becomes prohibitive once we have a big branching factor, and if we look at many steps ahead, because it's exponential. So one solution here is to not examine every node. Somehow we don't have to examine every node, and we'll see shortly why. But in particular, this is the key idea. We do not have to examine every node, and alpha beta pruning is doing exactly that. It's a solution to remove the computation of some nodes. And this is in particular, it's removing the branches that do not influence the final decision. So how exactly do we do that? So basically, the basic idea, of, as Professor Patrick Winston was saying from MIT, actually, is that so there's a quote from him: "If you have an idea that is surely bad, don't take the time to see how truly awful it is." So this is exactly what alpha beta pruning does. So imagine you have this small tree here with two moves here, so max and max min and max against a depth of 2. We have this state, so we have a 2, 7, 1 and something here. So let's look at in the first tree. So if this is a 2 and this is a 7, the min player will take the minimum between these two, so that's a 2. On this side we have a 1 and something else, and now the key idea is that we know that this node, because it's a min player, this node will be less than or equal to 1 because of this, because there will be a min between this 1 and something else that we haven't evaluated yet. And because we know that this thing would always be less than or equal to 1, we know that the max player, because it already has a state which is 2, it doesn't have, it knows that it will choose this optimal state regardless of the value here, basically, regardless of the value in this node. Can you see it? Can you see how this happens? Yeah. So basically, we don't have the result of this, that we don't have to actually evaluate this node. But even you can imagine it could be more. It could be a whole subtree behind it, not just a single node. It could be an entire big subtree. So we don't have to evaluate any of that subtree because of this. And no matter what it is, it won't affect the end result, no matter what the value here is. Yeah, question. Yeah, we kind of do from the bottom, but in a particular order. It's kind of, think of it like depth first search. Think of depth first search. So sort of we have a cutoff here, a depth cutoff. We start from the left-hand side, but because we obtain this value that here 2 that is higher than this one, higher than 1, then basically we can cut it off. So in some sense, it's a particular order in which we traverse the tree. Yeah. Exactly. Because we start bottom to top, but also kind of do it left to right, let's say. So it's that left to right that kind of, yeah, we can, yeah. Any other questions? No? Okay. That's a general idea of alpha beta pruning. So so we're computing the min value at a particular node n here, and we're looping over n's children. And of course, as we're looping over the n's children, the n's value estimate is dropping. Because here we're doing a min value, for example, at a particular node. And so the more we explore, the min will always take the minimum value. So that min will keep decreasing. And alpha is the best value that max can get at any choice along the current path. And if our node n becomes worse than alpha, max will avoid it, and so we can stop considering n's other children. So so this is our alpha value, for example. We know this alpha here. So in this graph, so now if you forget about the text, we just look at the graph. So this alpha is the best value that we found so far for the max node. And we keep going down the tree. And if this n is worse than alpha, we can simply avoid it. So because we know that even if you then it's a different subtree than alpha, because even if you keep finding it, then we will still choose alpha instead of this other path, if that makes sense. And similarly, we define a beta for min, for the min player. And the beta, again, will be the best node that the min player has found so far. And then if the current state of the current node that is currently being explored is worse than beta, then we don't explore it. So that's some a pseudocode of how alpha beta works. So so we have a max value function and a min value function, and these are very similar to the max value and the min value we showed just a few minutes ago. But the main difference now, so here what we had before was pretty much the same. So we initialize the value to minus infinity for each action. So we look at each action successor states. We compute the maximum over all those successor states. This is the maximum over the result of taking from state S taking an action A. And then you take the min value, we call it min value, which is basically running the function of the min player. And then we're taking the maximum over that. But this is what we add, these two lines we add for alpha and beta. So if the value, if the current value here is greater than or equal to beta, we simply return and break out of the loop. So then we don't compute any of these successes anymore. No, sorry, we don't take any of the actions into account. And so basically we break out of the function. And the same thing happens also in the min value function again. If the current the current value is more than or equal to alpha, then we break out, so we can skip evaluating some nodes. I know it can be a bit. It can be hard to kind of like get your head around it, but like I hope you got a bit of like the rough idea, and you can maybe look at this at home, like in your time, even if you don't get it now. But what I'm trying to highlight at least is the things that were added by alpha beta were these lines here. So this line, if v equals alpha, then return, and the same for that. That's where we break out the loop and we don't evaluate the rest. Questions? Yeah. When we evaluating the states of the tree. So when we evaluating like these states. So when you're going up, but also sideways, because you also explore like, let's say, left to right. You have a particular order, inherent order, in which you traverse the tree. So for example here, because imagine if you flip the tree around, like, if you flip this like that, then you could have started with this one. If the first state that this you evaluate is this, for example, you can do this part first, this left subtree first. But in that case, you wouldn't have pruned it, because well, it depends. It depends what the value was actually, but The order matters in which you do these evaluations. Sorry? We can a neighbor of who, like of the neighbor of this. The reason why this gets pruned is not because of this neighbor, it's because of this value of this 2. Because we know that this node is less than or equal to 1, and it's also because of this, yes. This node will always be less than or equal to 1, but because we've seen already something better, then we don't have to evaluate further, this thing further. That's why. So we must have to prune this. We must have seen this, and we must have evaluated this one. Without that, we wouldn't have been able to prune this one. Yeah. Okay. So here's another example. So we have our tree again. These are max nodes pointing up. These are min nodes pointing down. These are the alpha and beta values. We start with minus infinity and plus infinity. That's how we initialize them. So in the first instance, we actually recursively go down the tree. So how we how you actually implement it, we call this function. You basically call these functions recursively at each node. So basically, you're trying to compute the state of this node, and then that depends on the subsequent state and so on. So you call recursively these functions. This goes down all the way to here. So then now you made an evaluation. This was evaluated 3. So now our values get updated. So now beta becomes 3. We evaluated also this one at 12 and so on. But because this is a min state, we still take the minimum. So this doesn't get changed. It still stays at 3 as 3 and so on. This is an 8, and again this stays at 3. We pass it up to the update all the way to the root node. We explore another sub branch now with this one, and we know that since we had a 2 here, a value of 2, that this node will always be less than or equal to 2 because it's a min node. Because these ones can either be 2 or worse. So if they're higher, if these ones are 5 or 6, this will still be a 2 because we'll take the min. And because of this, and because now this node is a 3, which is higher than 2, then we can prune out these states, these subtrees. 3. So again, we explore then another subpath, 3 and 14, and so on. And you see how this one, because it was a 14, we could not prune it out because this is higher than this than all these other ones. So max could take this path. Max could take it. So we cannot prune it. So now we got a 5. We still have to keep on exploring because now the 5 is still higher than any of these 2. So we cannot prune in this branch. And now we got a 2. And now we are in a state where we can start pruning if there's more. Because now, basically, we know that this has to be less than or equal to 2. And we have a better option here with 3, for example. So if there's more nodes, we can prune them. So this gets updated to, so finally we get at the final optimal state is 3 for this. Yeah, which is taken by this one. Yeah. So why don't we do the alpha beta example now the same exercise so there's the same tree as before, but now let's do the same tree but with alpha beta example. So maybe even on the same graph you computed before, you don't have to redo it. Like circle out which are the nodes that will be pruned by alpha beta. Yeah, let's take another 5 minutes. There's a question, yeah? The order, yeah. Yeah, so assume left to right. Left to right, yeah, succession, yeah. How is the progress? How many of you have finished? Nobody yet. Okay. Okay, let's stop here. I wanted to hear, so how many nodes have you managed to prune? How, like, or let's say 4, 6, 10, 5 nodes pruned? Some more ideas, some other results? Throughout the whole tree, including the whole, so sometimes a whole subtree can be pruned, with multiple nodes. 10? Nice. Anybody else? What about from this side? Have any of you guys managed to prune any nodes? So it's a really, what I'm trying to, I think it's good we're going through this, because I hope some of you like are sort of like seeing how powerful this can be. We can end up pruning a huge part of a huge chunk of these trees this way, and to make a few remarks on this. So pruning does not affect the final results, even though we do cut out these trees. We still end up with the same values of the states in the nodes. It does not change at all. And we can also prune entire subtrees. So once we prune a node, the entire subtree won't be explored. And yes, so the ordering in which we traverse the tree can improve our pruning results. And this is actually order dependent, depending on which order we explore them. And in general, with something like a perfect ordering, the time complexity becomes b to the power of m divided by 2 instead of b to the m. So this is basically the same as the square root of b to the m. So one of the exponent to 1/2 becomes square root, basically. So this is giving us a branching factor of square root of b, which is amazing. So and in general, what this means is that the alpha beta pruning can look twice as far as minimax in the same amount of time. So we have we can basically do instead of looking at depth of 50, we can look at depth of 100 with alpha beta pruning on average, which is amazing. So and this is without making other approximations. We still get the same final results. Nothing that won't change. So and repeated states are still possible. You can end up in the same state, and that can be repeated in the tree. But we can of course like account for that with some sort of techniques in which we can store it in memory. But alpha beta pruning will not solve the repeated states problem, so you still get that. But it's more of a way to prune out based on the value functions and the min and the max iteration. Any questions on this? Okay. So yeah. Okay. So in that case, I think we're gonna stop here because we're gonna go into some other things that we've already gone quite. We finished early today, and good luck again with the assignments, and we'll see you on Wednesday. Yeah.
From last example, the class management working, like I have like a problem like understanding the whole process.
Yeah.
And I was wondering, like, is there like a video demonstration of anything that
Yeah, on YouTube. It's actually on YouTube. I found alphabet pruning and Minimax. Yeah. I looked at some. I found some on YouTube. They're quite nice. Yeah.
Okay, perfect.
Yeah. Have a look. Yeah.
Thanks.
Welcome. Yeah. Hi. Yeah.
So I emailed you a few weeks ago about being on the track team and trying to take this class, and I knew I wanted to come and talk to you about what I could do to stay on top of this class. I just bad planning on my part. I haven't had a chance.
No, it's okay. It's okay. Yeah.
So I was just wondering, like, what my biggest is like.
Yeah. What can you do to stay on top of the class?
Yeah.
Kind of just like do the worksheets and the quizzes and be up to date with all of that, like especially and also with the assignment, putting the assignment, of course, like do it as soon as possible because you can have time to even do more sophisticated things, kind of extra things. I would say that's the best thing.
Okay.
And the book, like kind of if you don't have some concepts, like I'm listing the chapters at the beginning of each lecture in the book in the Russell Norvig.
So reading through that.
Yeah, read through with that. Yeah,
okay.
Yeah.
Which TA is best father?
Both are good. Plus, also not only the TAs but also the graders. So Brian, who's a grader, and tutor. So he's also amazing. Like and he's the tutor before for this class, and he's taken the class himself. And so all of them, yeah.
I think that's all I had for now.
Yeah. So just kind of like it'd be good if you do all of these. Yeah.
Awesome. Thank you so much.
Yeah.
I appreciate it.
Hello. Yeah.
How the 1, 1, 1, 2 together.
Oh, so let me see the question. So after applying the unary, let's see. I know it's long. Do you mind if we come in the if you ask it in the office hour or like kind of, or go to the TAs because it might be better because they're more familiar with the worksheet and the programming assignment.
There is only one TA's time work for me actually.
Oh really?
Yeah, so that's why kind of like also wondering like kind of one of the sections since like we're building the section, so it's like we have to have time at those. Yeah.
What about Brian's? Because we have Brian is offering also like because apart from the TAs, he's really great. He's really great. If you go on the syllabus, I'm wondering. So he added also. Can you? Yeah, so you can make an assignment. Make a. Yeah.
It's like my Steve days. It's like already passed. Right. It's like this.
Is it this one?
Yeah, it's this one.
Oh, got it. Yeah. Let me try to go through it, but like I know it might take a while, and let's see. Can you go back? Let's go back. Yeah.
It's just like what I was thinking, like kind of my theory was like since here like 2 says one's for like must be adjacent to the B, and the other one is like must not be on the field, and B was like must be adjacent to the row, which means like for my understanding B has to be on either of those two. And C gonna be like if this B gonna add here, then C gonna be like around here. If B is here, then the C is gonna only this is the only option. It's like cannot be on the field. But in the answers here, it's like we are choosing the 1, 1, 1, 2, which means like those two are included in the answers.
Yeah, I get it. I have to read the question like in depth because I haven't read the question. So, well, I have office hours tomorrow. Like why don't I like have a look on it like like tonight, and like, if you wanna come, like, you cannot make it, no.
Tomorrow, I cannot come tomorrow. Yeah, it's like tomorrow your only office hour time.
Yeah, 4 to 6. So Why don't you post on Piazza? How about that? Post on Piazza. Yeah, post on Piazza, and that'll be the best. Yeah. Yeah.
Thank you.
You're welcome. You're welcome. Yeah. Do you have any other questions like about the material? Okay. This is the worksheet, right? Yeah. Worksheet too. Yeah. Nice. Yeah. Good. Do you have any questions? Here worksheet. Yeah.
For the band question.
Yeah.
Why following the consistency? Why can we just ignore the constraints? Because it says number one, the mass likely to play for the AI cool kids. Well, why is 8 p.m. a possible answer for the AI cool kids? But then if they're at 8 p.m., there's no time for the banana spark to play before them. Because two opening bands are at the same time. So why would that be possible?
Yeah. Again, I haven't. It's the first time I'm seeing the question, so I haven't managed to go through these. I'll have to read it. But why don't you do the same thing? You know, post on Piazza, and like because it'll take some time to kind of like go through it and stuff. Yeah.
They said they didn't read theirs. They emailed you or something.
Okay. Yeah. I didn't manage to look. Sorry. Oh no. So yeah. Got it.
Hi.
Hello.
I had a question about heuristics on questions 6 and 7.
Yeah.
Do it.
In the programming assignment or where?
Actually, the latest algorithm I've developed, it seems to be really complicated, and my friend is just looking at me. I was like, bro, is this even gonna work? The one that I've developed right now that wasn't admissible was I just added the distance between all the corners. But then I realized that wasn't admissible because all the distances, they're too big.
The task is to visit all the corners, right? Yeah. I mean,
how are we supposed to develop it on our own? I don't understand.
What do you mean? Like it's your homework, like it's your project. Yeah.
I know.
You have to do it on your own, like.
You're not going to give us any hints. So we're just meant to fail.
Sorry.
Actually, we can use anything inside of distance .py, right?
Mm-hmm.
So anything in there, even that one.
There's that one function. How do you use that?
We can extract. We're allowed to. We don't need to obey coding conventions. We can access all the variables, no matter how hidden they are. Right?
Yeah, you can. You can. Yeah. Don't change the signatures of the functions, because then that will break the autograder. But you can access them, like inside the signatures, like you can the code, you can like do the question. Yeah, do not change the signatures so that exist there already. But otherwise, yeah.
Question 7 takes more time than question 8.
Yeah. So you don't have to. So it might be a better idea actually to do 8. Yeah, if it's easier, and come back to 7. Yeah.
Having extensions.
No. But you have late days, so you can use them. So each of you have late days, but I won't give any extension. So make sure you use them carefully, because if you need them later on for programming assignment 2 and 3, you won't be able to have any left. Sorry. No, there's no. So those late days you're granted. So read the syllabus. There's no penalty for you. It's up to you to use them. It's for you to use them. But don't But that's more like, well, make sure you don't use them all, because then and if something actually happens, like if you get sick or something like that, like later on, like that's more like for these kind of cases like that. All the homework. Yeah, all the homework. I think I forgot. It is 3. No. 4. Well, P0, including P0 is 4, but without P0, yeah. The first one, I know the first one is long. The first one is long. Yeah, yeah. I think it might be the hardest. Yeah, yeah. Oh, yeah.
Like give us some stuff.
Here's something like because you can like think a bit about it, but also like consult with your colleagues. Like you're not allowed to share code, but you can like for example ask a bit like what are the strategies, good strategies to solve it. So you can consult with your colleagues. Like you can ask what are good strategies, for example, like for solving it. Like more like theoretically like that. You can speak to your peers.
Yeah, that's what I'm saying. So I'm asking you.
Like we can Google.
You can Google. Yeah, you can Google. Yeah. But there's just so many ways you can do that. I think that's the whole beauty because you can just think.
Gradient distance. Sorry?
We never touched those things like in 101, like which is the only prerequisite for this class before. Yeah, like we never been taught in 101. Right, and like the heuristic, it's like this is the first time we already touch it. It's like we already need to use those things like sort of like or can understand this heuristic in a short time. I need to apply it in the coding assignment without like any section, like any guidance.
But have a look. I know. No, it's fine. It's fine. So the thing is, like, I think it's useful to try them and see the behavior, like of the agent. And see how it fails because they're gonna kind of like I think that's things that I.
So how do we debug those things though? I'm like sometimes it's
look at the behavior, right? Of the agent.
Like, I mean, yeah, and of course look at the behavior, but how would we do that?
But which line I failed the task? It's like kind of hard to do the debug like that. I want to kind of one step, and then like to go like one step, like just kind of set the breakout point. Then like I can follow the code and maybe can like better understand my logic and like where it comes from. But the picture is like the gaming is like shining so quick. I sometimes I even don't know. Where the
I don't know actually if you might be able to run it slower, to change the frame rate, with the game. Might I actually don't know, but have a look into that.
And also I kind of want to learn how to like maybe like in specific line, like which line about the code.
You're gonna use a debugger.
Print statement.
Well, I don't use print. I use print statements and the debugger. I use both. Yeah, I use like if you're using VS Code, you can just instantly debug your code. That's really easy.
Professor, on the submission thing, it says submit to